Hi, this is Dr. John Bergdorf. In this video, we're going to introduce some basic concepts related to polynomials. Now, several other videos you're going to see will talk about using polynomials in various ways and doing various things with the polynomials. In this video, I just want to make sure that we have basic understandings of what the words are that are going to be thrown around in some of the other videos. So we will explore what is meant by a polynomial. But before we look at polynomials, we're going to look at something called a monomial. Now, a little bit of etymology, that's history of words. The word monomial is based on the prefix mono, which means one, and the ancient Latin word nomen, which means name. So a monomial, in literal sense, means one name. Well, what does that mean? Well, let's define it properly. A monomial is either a single real number, and that single real number can also be called a constant, or a single variable, or a product of a constant and one or more variables raised to whole number powers, known as exponents. So what are some examples of some monomials? Well, the definition says that a single number can be a monomial, so 5 is a monomial. A single variable can be a monomial, so at x, that would qualify as a monomial. Or a product of whole number constants times various variables raised to powers. 3x squared y, for example, or 7b squared c cubed. So we can have several variables. We could even throw in another one. Let's put a d in there too. Those are all examples of monomials. Within the monomials, the quantities that are multiplied together are called factors. So the factors in 7b squared c cubed d are the 7, the b squared, the c cubed, and the d. In any one of these monomials, the constant factor is referred to as the coefficient. So if you have a whole number by itself, the number itself is the coefficient. If you have a monomial with whole numbers and other things, other factors, it's the whole number constant that's referred to as the coefficient. The coefficient of this term is 3. The coefficient of this term is 7. What about that x? The x doesn't look like it has a whole number coefficient, but x can be written as 1 times x. So the coefficient of that term would be a 1. That's what's meant by a monomial and some corresponding ideas. Coefficients, factors, constants. Now, talking a little bit more about a monomial, the degree of a monomial is the sum of the exponents to which the variable factors are raised. Let's do an example of that. Suppose our monomial is 9x squared, y cubed, z to the 4th. The degree of that polynomial is found by looking at the sum of the exponents to which the variables are raised. I look at the exponents to which the variables are raised and I find the sum. Sum means add them up. So the degree is 2 plus 3 plus 4. 5 plus 4 is 9. Now, many of our monomials that we're going to look at are fairly simple with only one variable in them, like this one, 8x squared. Well, the degree there would just be the single exponent. The degree of that monomial would be 2. Now I'm going to see if I can fool you a little bit. Let's look at this monomial, 3 squared ab squared. Now, if you want to think about that for a minute, if you give me the answer that the degree is 4, 2 plus 2, I definitely see where that's coming from, but you have fallen into my trap. Notice that in the definition it says that the degree of a monomial is the sum of the exponents to which the variable factors are raised. So I would not be paying attention to the 2 to which the 3 is raised. That's not a variable raised to an exponent. In fact, what I would almost certainly do is say, well, goodness gracious, 3 squared is really 9. And so the exponent on the 3 is not considered. Now, there doesn't appear to be an exponent on the a, but that could be an understood 1. So if you have a single variable, not raised to a power, think of that as itself to the first power, so that the degree of this monomial is actually 1 plus 2 equals 3. So that's a little bit of a surprise there. Here's another surprise. What if we have just a whole number? There's no variables at all, and if the degree is the sum of the exponents to which the variable factors are raised and there's no variables, what are we going to do? Well, we say that the degree of a constant, like 11, is just understood to be 0. So the degree of 11 is 0. Now, let's move a little bit farther. Binomial. So we have monomials and binomials. Now, bi is a prefix that represents 2, and so a binomial is the sum of 2 monomials. The 2 monomials are referred to as the terms of the binomial. So let's write some examples of that. Here's an example of a binomial. 3x squared y plus 5z to the third. It's a sum of 2 monomials. The 2 monomials within the binomial are referred to as its terms. Pretty simple. One small trick, perhaps. Suppose we have 7x squared minus 5x. Now, the word sum in the definition refers to addition, and there's no addition here. Well, actually, really there is. We're going to assume that a subtraction can be written as the sum of a negative. So 7x squared minus 5x is the same thing as 7x squared plus negative 5x. Now that's significant because when I'm thinking about the terms of this binomial, this is a term, this entire thing is a term, including the negative 5. And that will become relevant when I refer to the coefficient of that term. The coefficient of the second term would include the negative sign, and that will become relevant at various points in this course. So that's a binomial. Monomial, 1 term, binomial, 2 terms. So it probably will come as no surprise that a trinomial is a sum of 3 monomials. An example of that would be, for example, 4x squared minus 3x plus 5, which we'll write, or we'll think about as 4x squared plus negative 3x plus 5, so that the coefficients of this trinomial are 4, negative 3, and positive 5. Now, we could talk about quadrinomials and pentanomials and hexanomials and on and on and on and on and on. But at some point, that just seems to get a little bit tedious. So we really don't use those terms. We talk about monomials, binomials, trinomials. And then we have a more generic term. This is where we finally have been trying to get to so far. And that's the idea of a polynomial. Poly is a prefix that means many, many terms. Now, the etymology of that word is a little bit misleading. When you look at the definition, you'll see this. a polynomial is either a single monomial or a sum of any number of monomials. So if I want to make some examples of polynomials, this would be one, 5a squared b cubed. And you might say, wait, that's a monomial. Yes, it is. It is both a monomial and a polynomial. So a little bit of a surprise, but a single monomial is a polynomial. More often, though, a polynomial is referring to many monomials added together. A trinomial would qualify as a monomial, so the example we did right above this, that's a polynomial too. It's also a trinomial. But also polynomials that have more terms. So here's one. 3x squared minus 4xy plus 5y squared plus 3z minus 2. That's a polynomial as well. And again, we don't use a fancy name for it. If it has more than 3 terms, we would just say that this is a polynomial with 5 terms. And that is more than enough. Okay, basic definition: monomial, binomial, trinomial, polynomial. Now, we talked about the degree of a monomial a little while ago. That was the sum of the exponents on the variable factors. We also talk about the degree of a polynomial. The degree of a polynomial is the largest of the degrees of the monomials that comprise the polynomial's terms. Well, let's look at that a little bit more carefully. Here's an example of a polynomial. 4x cubed y squared plus 5z to the 5th y minus 3 plus 2x squared y squared. Now, looking at the definition again, the degree of the polynomial is the largest of the degrees of the monomials that comprise the polynomial's terms. Here's what you do. You look at each term individually and you figure out what each term's degree is. Remember that this is the sum of the exponents on the variables. So this degree would be 3 plus 2 are 5. The first monomial, the first term, its degree is 5. If we understand the y in the second term to be y to the 1, then the degree of this monomial, this term, is 5 plus 1 equals 6. What was the degree of a constant again? 0. And the final term, adding up the exponents, we have 2 plus 2. The degree of that term, that monomial, is 4. So you look at the degree of each monomial, and then you take the largest one. So the degrees of the monomials are 5, 6, 0, 4. The biggest one is 6. So we say the degree of the polynomial is 6. Now, many of the polynomials we're going to look at are not really quite that complicated. Often there's only one variable. So if I had something like 3x cubed minus 7x squared plus 5x plus 2, for example, the degrees of the individual terms are 3, 2, 1, and 0. The largest of those degrees is 3. Very straightforward. Okay. Now, before we leave talking about polynomials, we need to talk about like terms in a polynomial. Like terms become very, very important. And terms are called like terms if their variable factors are exactly the same, including their exponents. And we'll get to those last two sentences later. So what if we had as a polynomial 7x squared plus 5x plus 3x squared plus 9? Let's see what we mean by like terms. Terms are called like terms if their variable factors are exactly the same, including their exponents. Look at these two terms. Exactly the same variables, exactly the same exponents. 5x is not like the 7x squared and the 3x because although it has an x like the others two have, it does not have the x squared. The exponent is different. Now, if you have like terms, they can be combined. Think of them as like objects. Lots of times I say, imagine that like terms are like apples, and you can combine apples. Unlike terms are like oranges. You can't combine apples and oranges. But if you look at it this way, you have here in your 7x squared, you might think of that as 7 apples and 3 more apples. Now, if you have 7 apples and you have 3 apples, you can put them together and say, oh, well, that means there'll be 10 apples. 7 plus 3 is 10. So I could write this polynomial much more simply by saying 10x squared. Now, can I combine the unlike terms? That's like oranges. 10 apples and 5 oranges is 10 apples and 5 oranges. You can't really combine those. So if the terms are not alike, you can't combine them. And the important thing to observe here is that although this polynomial in the beginning looked like it was going to have 4 terms, because 2 of them combine, you really only have 3. It's a trinomial. Let's look at one more of these just very briefly here. 3x cubed y squared plus 5ab squared minus 8x cubed y squared. So put a line here to separate these. Do we see any like terms? They have to have exactly the same variables and that they have to be raised to exactly the same powers. These two terms are alike. Notice I'm circling the negative because the negative is part of the coefficient. So when I combine these two, I'll be looking at 3 of them minus 8 of them. And I have to think about negative numbers. 3 minus 8 is going to be negative 5 of my, quote, apples. Negative 5x cubed y squared. And then the 5ab squared is an unlike term. It cannot be combined. But I can combine the like terms. Now, the notion of apples and oranges, and you can combine apples and oranges, is really just fine to get a basic understanding about how like terms work. If you want to delve a little bit deeper, there is a more profound reason that like terms can be combined. And it's based on the distributive property. Now, the distributive property is a property of numbers. Its full name, its full legal name, is the distributive property of multiplication over addition. And what that property says is that if you have any three numbers, any 3 real numbers, a, b, and c, and you have a multiplied by the sum of b plus c, the a in the multiplication distributes across the addition. So you have a times b plus a times c. Multiplication distributes over addition. Now that's true whether the multiplication is at the beginning or at the end. Same thing happens here. The a in the multiplication distributes across the addition a times b plus a times c. Either way. So how is that relevant to combining like terms? Well, let's say you have 3x squared plus 5x squared, and we know those are like terms. If I look at the second formulation of the distributive law and I read it backwards, I see that I have an x squared that is mentioned in both places, much like the a is. And so the distributive law read backwards would say that I could, and this is a term we use, and you'll hear it much more often, that we can factor out the x squared. See how that works? You might want to read it in reverse to see that it really does work. The x squared gets multiplied by the 3, that's 3x squared. The x squared gets multiplied by the 5, that's 5x squared. I'm sort of doing that distributive law backwards. Now, if I do that, then I can say, oh, what? 3 plus 5 is equal to 8. And so 3x squared plus 5x squared is 8x squared. And you might say, gee, I was happy with the apples. And that's fine. That is absolutely fine. This just shows that there is a mathematical reason that combining like terms works using the distributive property. So in this video, we have found out what some basic definitions related to polynomials are. And in future videos, we'll talk about multiplying polynomials, adding them, subtracting them, factoring them, and doing many other things. Thanks. Bye-bye.